Swayam Prabha. Digital India. Educated India.
Then we introduced displacement field and then displacement gradient tensor for solids, first for 1D, 2D and then 3D. And what was the definition of displacement gradient? We consider two adjacent particles and then take the difference in displacement of two adjacent particles, divide by the distance between the same particles. We also said that the two particles can be considered along x, y, z directions and the displacements could be in x, y, z directions, and hence the displacement gradient is a tensor. Now let us see how do we extend that for fluids. Okay, this part is same as what we have seen in the last slide. For solids we have displacement gradient, difference in displacement of two adjacent particles divide by distance between the same particles, okay, and this is the displacement gradient tensor. Now for the case of fluids, let us define the velocity gradient. How do we define velocity gradient? Instead of displacement, now we take velocity. So the definition is difference in velocity of two adjacent particles divide by distance between the same particles. Okay. Now you can analogously write the velocity gradient tensor. Once again it is a tensor. The reason is we can consider the particles along the x, y, z directions and the difference in velocity can be along once again x, y, z directions, resulting in a velocity gradient tensor. Okay. Other way of explaining is that velocity itself is a vector. There are three components. Now you are looking at the gradient of that velocity component that could be in three directions, resulting in a tensor. Okay. Velocity in three directions and the gradient in three directions, resulting in 9 combinations of directions, resulting in a velocity gradient tensor. Okay. Then what we did in solid mechanics was, having discussed strain and discussed displacement field, displacement gradient, we expressed strain in terms of displacement gradient, and we are going to repeat the same exercise here, but now find relationship between strain rate and then velocity gradient. Okay. This is the diagram which you have seen. This is the diagram which you have discussed to relate strain and then displacement gradient, where we initially took a 2-dimensional plate or a 2-dimensional region of length delta x, delta y, and then it was subjected to a force, and so there was translation, rotation, normal strain, shear strain, meaning change in length and change in angle as well. Okay. So PQRS became P star, Q star, R star, and then let us say S star. Okay. And we also noted the displacements of all the points. For example, Ux at x comma y is a displacement of P, x displacement of P, and Ux at x plus delta x comma y is a x displacement of Q, and Uy at x comma y is a y displacement of P, Uy at x plus delta x comma y is a y displacement of Q. And we derived the relationship between normal strain and displacement gradient. So let us quickly recall that, so that we can easily understand the relationship between normal strain rate and velocity gradient, which we are going to derive in the next slide. Okay. Normal strain is defined as change in length by original length. We are considering a line element along x axis and hence it is epsilon xx. So, limit delta x tends to limit delta x tending to 0, okay, and p the element line element p q has become p star q star. So, length of p star q star minus length of p q divided by length of p q. Then we said we are going to assume infinitesimal rotation. So, we said the length of p star q star is same as the projected length of p star q star. So, length of p star q star becomes the difference in the x coordinate of q star and then p star. For q star the x coordinate is the old x coordinate which is x plus delta x plus the displacement of q which is ux evaluated at x plus delta x comma y. Coming to p star, the x coordinate of p star is the old x coordinate which is x plus the displacement of p which is ux evaluated at x comma y. So, the term within square bracket gives the length of the projected p star q star, and delta x the length of p q and divide by length of p q. Okay. Of course, limit delta x tends to 0, limit delta x tends to 0. Okay. X cancels out, delta x cancels out, and we are left with only these terms ux at x plus delta x comma y minus ux at x comma y divided by delta x. When you take limit delta x tending to 0, we get dou ux by dou x. So, what we have done is related normal strain to the displacement gradient, namely dou ux by dou x. So, now okay, see analogously we derived relationship between shear strain and displacement gradient, okay, where we derived gamma xy is equal to alpha plus beta as dou uy by dou x plus dou ux by dou y. We also derived relationship for rigid body rotation, and we defined that as average of rotations of two perpendicular line segments. We took into account the sign as well, okay, and we got the expression omega xy is equal to half dou uy by dou x minus dou ux by dou y. So, one is anti-clockwise, other is clockwise. So, we take into account the sense of rotation. Okay. So, now we are ready to derive the relationship between strain rate and velocity gradient. The same figure is shown here, just colored in blue to get a feel that we are looking at a fluid element. Let us see how do we derive. Okay. The normal strain rate is rate of change of length per unit length. Okay. Change of length per unit length is the normal strain, rate of change of length per unit length is the normal strain rate. Okay. How do we understand this normal strain rate, so that it will be easy to derive? Suppose if you have a rod like this, and just imagine that the length keeps increasing, then at any instant of time the rate of change of length divided by the instantaneous length is the normal strain rate. Okay. Or let us say there is a thread which keeps increasing with thread whose length keeps increasing with time. You have a thread and then that keeps increasing with time. Then how do you define normal strain rate? The rate at which that length changes, which is dl by dt in the nomenclature shown here, divided by the instantaneous length at any instant of time, that is the normal strain rate. Okay. So, how do you rewrite it? You can, so dl by dt by L is the normal strain rate. How do you rewrite this? How do you rewrite it? dl by L by dt. So, this will help us to understand. Now, we are going to apply this for this small line segment PQ. Okay. let us do that. So, epsilon dot xx, why is it epsilon dot xx? Epsilon xx is the normal strain, because we are discussing normal strain rate, it is epsilon dot xx. Okay. Now, instead of L, I have written this expression in terms of delta x, because delta x is equivalent to our L. Okay. So, d delta x by dt divided by delta x. Now, the d which is used here is capital D by dt, the d by dt which is used here is capital D by dt. The reason is this derivative is taken following the fluid motion. Remember, this line PQ is in a fluid, and the rate of change of its length is determined by following its motion along with the fluid. That is why we take a substantial derivative d by dt, and as we have rearranged here, this expression is also rearranged d delta x by delta x divided by dt. Okay, now, okay, so how do you express this? D delta x by delta x is change in length by original length. So, it is length of p star q star minus length of p q by length of p q in the limit of delta x tending to 0. Okay. The limit of delta x tending to 0, which means p and q are very close to each other, and then we need a rate of this. So, divide by delta t and then take limit delta t tending to 0. So, this is the expression for the normal strain rate for a line element along the x direction. Okay. So, now let us express this change in length by original length exactly as we have done earlier. So, this expression is exactly same as what we have done earlier in terms of displacements. Okay. Now, the difference comes, we have to express the displacements. Remember, these are in terms of displacement. Okay. That is why we had a quick recall of derivation of normal strain. Now, these expressions are in terms of displacement, we will have to express in terms of velocities. So, what we will do? We will express the displacements in terms of velocity into delta t. We consider small time interval delta t, very small time interval delta t. Over the time interval, we express the displacement as the velocity into delta t. That velocity is some average value over the delta t. Okay. So, ux at x plus delta x y is expressed as Vx at x plus delta x comma y into delta t. Okay. Displacement is equal to velocity into delta t, that velocity is averaged over that time interval, small time interval delta t. Similarly, ux is also written as ux at x comma y is written as Vx at x comma y into delta t. Okay. That is the step which differentiates this derivation. Okay. Okay, now x cancels out, delta x cancels out, okay. And then what we have is limit delta x tending to 0, Vx x plus delta x comma y minus Vx at x comma y divided by delta x, and of course, you have delta t in the numerator. Okay. Now, what happens? This becomes, of course, delta t cancels out and this becomes dou Vx by dou x, and so epsilon dot xx is equal to dou Vx by dou x. But now, you should note that just you are cancelling delta t and you are taking limit delta t tending to 0, which means that the velocities become instantaneous values. That is the difference between this step and this step. When you take cancel out delta t and when you are taking delta t tending to 0, these two velocities were average velocities over some time interval delta t, but now we are taking delta t tending to 0. So, they become instantaneous values. So, now this gradient of velocity is gradient of instantaneous velocities, and as we expect this, the relationship is valid at every instant of time and also at every spatial location. Why at every spatial location? Because we have made delta x tend to 0. Why instantaneous? We have taken delta t tending to 0. So, the relationship between the normal strain rate and velocity gradient is given by epsilon dot xx is equal to dou Vx by dou x. Okay. If you compare with the corresponding relationship for solids, which is normal strain is equal to the displacement gradient. Okay. So, if you want to let us say vaguely say it is just time derivative on both sides, that is a little crude way of saying that time derivative is of course substantial time derivative, but for quick understanding, if you compare epsilon xx, left hand side you have epsilon dot xx, right hand side we had displacement gradient, now we have velocity gradient. Okay. So, in one way it is just time derivative on both sides. This I would say crude viewpoint will help us to extend analogously all the relationship, though we have done the derivation in detail, and this will help us to understand the to write the expressions analogously. Okay. Of course, this animation has been going on, which shows, which I have seen already, shows that the length of line segment AD keeps increasing and length of line segment AB keeps decreasing. Okay. This rewritten from the last side, normal strain rate epsilon dot xx is equal to dou Vx by dou x. Now, as we have discussed, we can now quickly write the expression for shear strain rate, which is gamma dot xy shear strain rate, and then earlier we had dou uy by dou x, now it is dou vy by dou x, and then we had dou ux by dou y, now it is dou vx by dou y. So, once we understand that is just time derivative, okay, for quick understanding, then we can analogously write all the expressions. You can also introduce epsilon dot xy, just like we had epsilon xy, which is gamma dot xy by 2, which is shear strain rate by 2. So, above expression divided by 2. Okay. And of course, we have these animations, one for normal strain rate, the left hand side, and the right hand side is for shear strain rate, one in which one for normal strain rate the left hand side, the right hand side is to illustrate shear strain rate, and one in which the length keeps increasing or decreasing, other in which the angle decreases with respect to time. Okay. Once again want to mention that the shear strain rate is always with reference to two line elements which are perpendicular to each other. Okay. Okay. So, only the initial at time, let us say whatever time t, where we have two perpendicular line segments and the angle decreased between the two line elements, that rate of change of angle is a shear strain rate. Okay. It is not applicable throughout the motion of the fluid element. Okay. We can also relate rotation rate and then velocity gradient. We said for the case of rotation, we define it as average of rotation of two perpendicular line segments. Now, it is very simple, average of rate of rotation of two perpendicular line segments. What does it mean? The rate at which, let us say if you consider two line segments PQ and RS which are perpendicular to each other, rate at which PQ rotates plus rate at which PR rotates, average of these two is the rotation rate. Of course, taking into account the sense of rotation. So, rotation rate is equal to omega dot xy earlier we had omega xy, now omega dot xy, and this expression is analogous to what I had written earlier. We had dou u y by dou x, now it is dou v y by dou x. We had dou u x by dou y, now we have dou v x by dou y, of course, and a minus sign and then a half.